derive the equation of motion from a linearly viscous fluid. The equation of motion, the general form, is given by what we aim to do now is to reduce this to in Cartesian coordinates for a linearly viscous fluid, for which the equations are follows. This is for a linearly viscous compressible fluid, and this is for an incompressible linearly viscous fluid. So we see that in this case, if I want to calculate the divergence of T, first I have to calculate the divergence of a tensor, which is given by some alpha times I. Alpha is a scalar which could depend on x as well as t, position as well as time. We show that this is equal to the gradient of alpha. Right? So the divergence of a tensor, the unit tensor, which is multiplied by a scalar alpha, can be easily shown to be the gradient of the scalar. And we've already seen. So now what is left is to calculate the divergence. These two are easily calculated now. What I am required to do is to calculate the divergence of D, because I am assuming that to be a constant, be independent of the scale. So all I need to do is to calculate the divergence of this. So again calculate the ith component of that. So this is clearly so dji equal to dij. So I can write it in whichever way I want. And this is already a derivative in dji or dij. There's then a further derivative. So I write this in expanded form as d by dxj times half of dvi by dxj plus dvj by dxi. That's what the comma j means. Comma j means d by dxj. That is now acting on the ji element of dji, which can be written like this. So ij, limit of ji, it doesn't matter. Whatever it is, so I don't have to worry about the sign here because both are added. Because for omega, I have to be a bit more careful how I write which comes first. So then, this can be written as half d by dxj acting on d by dxj di twice plus I can write the other one as d by dxi by interchanging we can write it again first d by dxj. So what is this? D by dxj. It's important that you should not convert it d squared by dxj squared. That will be totally wrong against the meaning because the repeated index summation convention is an operation. Right? D by dxj, the Laplacian of di. So Laplacian in rectangular coordinates is d squared by dx1 squared. D by dxj of d by dxj is simply this. D by dx1 acting on d by dx1. D by dx2 because the sum is over j here, not over I, because I am looking at the ith component of the divergence of d. So that is half of this. If I interchange the order of differentiation, I get d by dxi of dvj by dxj. So what is dvj by dxj? Huh? No? Yeah. dv by dxi of the divergence of this is the ith component. So clearly now I can write the divergence of D as half times the Laplacian of the vector D plus the gradient of the divergence of D. It's fairly straightforward. So now we'll focus on the compressible fluid, because the compressible fluid, if I put the divergence of the velocity to be 0, I get the equations for the incompressible fluid. At least to get the equations, that procedure is fine, but you have to always remember the different role played by the pressure in the compressible fluid as opposed to the incompressible fluid. So there is a big difference in the way you solve the equations. So now everything together, right? So we get for the is equal to, for the compressible fluid, I can write the body force unspecified and the divergence of this. So this is going to give minus for the compressible fluid. That will be the first term, and then we get maintaining lambda to be a constant, right? So plus 2 times the viscosity times the dynamic viscosity times the divergence of D, which is half times the Laplacian of plus so I have combined these two. The gradient of the divergence of D has 2 terms, so that will become compressible fluid, and then is equal to the right hand side will be equal to much simpler form for the incompressible fluid. What I will first consider only the flows of the incompressible fluids. Right? So for the incompressible fluid, I will write down the equation in full component form, because this is still in vector form. So if I were to write the ith component of this vector equation, so I am now writing this, the incompressible fluid, the ith component of the equation of motion can be written as minus plus the viscosity term. Right? So this is for the incompressible fluid. Now we can look at what this would be for the what is often referred to as an inertial term. It's part of the inertial term. V dotted with the gradient of V.
Gradient of Ravi. Gradient of Ravi.
No, I that will come if I were to combine this. So this is just Vj, the ith component, right? Ji, so that would be Vj, Vi, comma j. Right? So if I were to expand this, this would have the form V1 dvi by dx1 plus V2 dvi by dx2 plus V3. So I can write this as rho dvi by dt plus, so the Vi comes here, then it's summed over j equal to 1 to 3, right? So the ith equation will have the velocity component appearing within the derivative. That's an easy way to remember this. I can further write this as full form as this has to be solved for the incompressible fluid in combination with the continuity equation, because there are three variables here, V1, V2 and V3, and also the pressure. We need another equation, and that will be given by I equal to 1 to 3 plus the continuity equation, which would be simply dv1 by dx1 plus dv2 equal to c. So we have now we consider some special cases of flow. The simplest flow that we consider is what is often referred to as a one-dimensional flow. Somewhat misleading. What we often refer to as a one-dimensional flow is that two of the velocity components are zero, only one of them is actually non-zero. Okay. So I could choose any one of them to be the non-zero component. So V1 equal to V2 equal to 0, and V3 is non-zero. Right? V3 to be non-zero. So now what you see here, this is one-dimensional flow. First, if I apply the continuity equation to this particular case, we get that dv3 by dx3 equal to 0. That means v3 cannot depend on x3 for one-dimensional flow. Further simplification will arise if I now look at, for instance, the inertial. So we also look at steady one-dimensional flow. We are really not going to consider unsteady flows for a large part of this course. We focus on steady flow. So steady flow would mean that this term is zero, so no variation with respect to time. That's the only place where the time variation comes in. Right? So steady flow. So if you look at this inertial term for one-dimensional, right? You will see that if we consider I equal to 1 or I equal to 2, both of them will mean that these, because this is really the heart. If you look at this equation, right, the non-linearity is coming in the so-called inertial term, V dotted with the gradient of V. So an inertial term is referred to as inertial term, because all of these are linear terms in the velocity, as well as the pressure appears as a linear term. It's a set of linear equations, except for the inertial term. Non-linear always a problem in solving the equation. Right? First of all, very unlikely analytical solution will be readily available, non-linear, unless in some special cases. Right? So non-linear, this is often a source of problem in solution. But you will find that for one-dimensional flow, where only one of the components of the velocity is non-zero, and we will find the inertial terms identically vanish, and you can easily check that because from I equal to 1, 2, right, dV1, so V1 and V2 are identically 0, any derivative involving them will also be 0. So inertial terms would vanish, and steady flow and already getting rid of the unsteady state term. Now if you look at I equal to 3, there of course dV3, right? And V3, what this means is that V3 is a function only of x1 and x2, right? So I have dV3 by dx1, dV3, so I equal to 3. So you see that for dV3 by dx1 and dV3 by dx2, which need not be 0 in the general case, they are multiplied by V1 and V2, which are 0, right? So this is 0, this is 0. V3 is there, it's of course non-zero, but continuity equation says that dV3 by dx3 has to be 0. So for I equal to 3 also, the inertial term vanish. So we get a considerable simplification of the equation of motion for so-called one-dimensional flow. They can be written as in the following way. So we have V3 not equal to 0, that's arbitrary. I can also choose V1 or V2 to be not equal to 0. Whichever component is non-zero, I am choosing it to be the V3. Right? So now if I write the steady one-dimensional flow, incompressible linearly viscous fluid, all these two equations you have to keep in mind. Constant viscosity, linearly viscous, incompressible, constant viscosity. For all those cases, the continuity equation is again utilized, right, and simplified. The equation of motion will mean that for I equal to 1 to 2, the entire left hand side would be 0. So I will get I equal to 1 would be 0 is equal to rho V1, that is the component of the body force in the O1 direction, minus dV by dx1. That's all. Right? Because V1 and V2 are 0, so I won't get the viscous terms also. It's the simplest possibly case you can consider. So I equal to 2. And so I equal to 3 is when the left hand side will continue to be 0, steady flow, and all we have shown that the inertial terms will vanish. And we get 0 equal to rho d3 minus dt by dx3, whereas that, so d3 cannot depend on x3. Okay, this is identically equal. So that means at one point the derivative vanishes. Identically is equal. Okay? So that means d3 can depend only on x1 and x2. So that means the second derivative of d3 with respect to x3 will also be 0. So we get a simple set of equations. We will apply this to a very simple case. So simple cases of flow in rectangular channels. You will soon see that they are limited by the fact that these equations are in the rectilinear coordinate system, and we are not in a position to handle for the flow through it. Even the simplest case of a flow through a tube, which will lead to the Hagen-Poisson equation, we cannot really handle because we don't know how to write the equations in other coordinate systems. It will be very complicated to solve the problems in the rectilinear Cartesian coordinate system. Right? So that we have to go into how to transform the general equation of motion and the continuity equation in arbitrary coordinate system. We'll see how to do that later. Arbitrary curvilinear coordinate system. The only restriction we have for this course is that those curvilinear coordinate systems also have to be orthogonal. That will be restricted. Otherwise, the problem becomes even more complicated. But the cylindrical and the spherical coordinate systems are the ones that we will focus on in this course. So the first initial part, just going to consider one-dimensional flow, very simple cases involving where the rectilinear coordinate system equation can be directly applied. So for that, I will consider the very well-known example of flow of a falling film down an inclined plane. So this is the inclined plane, and there is a certain bend, and there's a film. This is the flow of a liquid. It's incompressible and linearly viscous. We'll assume the film thickness remains constant, low. The flow of a film. So this is all filled with fluid. It's going down an inclined plane, right? And we'll assume that the inclination with the vertical is given by some angle beta. So we'll assume one-dimensional flow. So the coordinate system has to be chosen following the one chosen in Bird's relation. It's a very standard problem. So any number of those we have this. So I'm taking this to be x and this to be z. Y would be the direction perpendicular, would be the correspond to the width of the plate. Right? So the plate is assumed to be quite long. We have flowed down the inclined plane. So we will assume one-dimensional. So we assume that B is equal to so automatically that would mean that this is x, y, z. That is how it is. So we have now made the transition. So I'll make x1 to be x, x2 to be y, x3 to be z. That also we have to contend. Most of the problems in the books are in the, they don't call it x1, x2, x3, they call it x, y, z. Right? So we have to make the connection. So what we get is that from the continuity equation we get dz to be dz of simply x and y. dz by dz would be 0 by the continuity equation. So we are now in a position. The only thing is that we have to now resolve the body force. The body force is given by g, but it is not quite in the z direction. It's the vertical direction. This is the body force per unit mass. Acting in the vertical direction. So clearly, we see that V is equal to, we define it as G. We see that Vz is equal to G cos beta, and Vx is equal to, in the negative x direction, minus G sin beta. And G, Vy of course would be 0. We see how these equations are to be applied in these cases. Right? So now I can write this as Vx. Only one component is in operation. So we can now transform these equations. So rho minus rho t sin beta minus dv by dx is equal to 0. That is the first equation. The second equation is that root dy is 0. So minus dv by dy is equal to 0. That means the pressure is independent of y. No variation of pressure in the y direction. So the last equation would be viscous term, this is clearly the important equation. Other equations can be give us a way to obtain the pressure actually. We have this. So now for the first, typically what is also done further, so this is all the equations say, but now further assumption is made that to neglect this term in comparison with some dimensional analysis can be done, and based on the fact that the thickness of the film in these cases is much smaller than the width of the film, you can make a dimension. To make a dimensional analysis, the characteristic length along the x direction is delta, and that along the y direction is double. So we transform to dimensionless variables, right? Then you can easily verify that the ratio of these two terms would correspond to w squared by delta squared, or rather you will get a delta squared by w squared term multiplying this derivative in the dimensionless coordinates. So based on that, you can argue that the variation of Vz in the y direction can also be neglected. So that's a further assumption we are making. So we assume that this is equal to 0. So this has to be distinguished with the non-dependence of Vz on z follows directly from the continuity equation. That is not an assumption. The moment you say that I am neglecting all the components other than Vz, automatically the continuity equation to be satisfied, we cannot have any variation of Vz in the z direction. Right? So that is not an assumption. That's also following from an assumption of one dimensional flow. But that is dictated. Once you have made that assumption, it's dictated by the continuity equation. However, this is a further assumption I am making based on physical arguments or whatever. Simply we have to retain that term. And typical solution of these problems, you neglect that also. So we get this. So this is the final set of equations we have. So obviously these are the equations that we first would look at. So this would mean that E is equal to and then I am also get that dP by dx. So I can solve for the, try to at least solve for the pressure. So important thing now to remember, which we haven't discussed at all, is the question of boundary conditions. Because we were assuming steady flow. So the question of initial condition doesn't arise, but when you're having dependence on the position, so you have to see that you all know that if you have a second order derivative, then we need two conditions. The pressure has only first order derivative. You need only one condition on the pressure, whereas you need two conditions on the velocity component Vz with respect to x. We'll see now what those conditions are. So from this I get that V has to be dependent on x and z only, is independent of y. If I use that here, then I get dP by dx is equal to actually a constant. That's a constant. So I can integrate this. Plus what? Plus some function of z, right? Because it cannot be immediately taken to be a constant because it's only a partial derivative, right? So we've already seen this kind of an argument in earlier courses. Suppose I leave it as a constant. The question is, whether the equation is satisfied or not. Clearly the equation is satisfied because if I differentiate it with respect to x, I recover the differential equation. But also, if I, let's say, assume that whatever that is a function of z, Then also the differential equation is recovered. I differentiate this with respect to x, dp by dx minus rho t sine theta plus p naught of z. In both cases, there is a constant or if that additional quantity is a function of z, the differential equation is satisfied. Obviously, we have to take the more general case because we are looking at this as the most general solution, right? So, if we just leave it as a constant, and if actually that turns out to be a function of z, we get an incorrect expression, not completely correct. Only one part would be correct. The dependence on x would be correct, but we would miss the dependence if any on z, right? However, typically the assumptions that are made in this kind of a problem is to make that function to be a constant, because if now we need a boundary condition to find this function. Typical boundary condition is that T equal to P atmosphere at x equal to delta for all z. It's sort of negative. There is a certain height variation, but we assume that the atmospheric pressure is acting uniformly on the surface of the film for all z. And that would mean we get P atmosphere is equal to minus at x equal to delta, that is at the surface of the film, plus P naught of z. And P naught of z then turns out to be P atmosphere plus rho t sine theta delta, right? Which is actually a constant. It's not a function of z. That is what we obtain for the special case corresponding to this boundary condition. Right? So we get that, and then I can also find the pressure within the constant, but that constant is given to me, P atmosphere. So I can write this as P atmosphere plus rho g sine theta times this is almost like a hydrostatic pressure, because delta minus x is the height below the surface, right? So just getting added, the atmospheric pressure, on top of the atmospheric pressure we are getting rho g z, but here because the plane is inclined, we are getting the component of g in that in the x direction actually. So that is the height. Sort of, we just focus on the values of the inclined plane. The height is given by the variation of the x direction, but the hydrostatic pressure is here exerted by the component of the acceleration due to gravity in the x direction. So that's why the rho g h or rho g whatever we are getting here, rho g sine theta. So the pressure is now determined, and we are now ready to solve the of course equal to 0, right? So what we get is that dE by dz is actually 0, right? So that's what we are getting. So this term would vanish, and so the equation simplifies to this. Right? Because we have found, based on the boundary condition given to us for the pressure, it's independent of z also. So it's dependent only on x, and so we finally get this very simple equation. Actually a constant coefficient equation, very, very easy to solve. I'll just integrate it once, and I'll get x plus, now the constant would be simply V is a constant. The Vz is actually now it's become a total wave. Vz is actually a function of x alone. And effectively, what we are having is this. Partial derivative vanishes because initially we started out with Vz being a function of x and y, right? Then we neglected the dependence on y, so we're getting Vz to be a function of x alone, right? So we get this plus C1, and when integrate it a second time, and we get plus another constant. So there are two constants, and so we need two conditions to determine the two constants. So now, if you look at this, you have to look at the variation is all in the x direction. So the boundary of the fluid, if you look at it, one boundary of the fluid is actually in contact with the solid surface. The other boundary is you have, let's say, air. This is some solid wave. So we have the two interfaces where the fluid, a liquid, is in one case in contact with the gas, another case in contact with the solid. So when a liquid is in contact with the solid, usually, right, liquid solid, usually the so-called no slip, that's called as a no slip condition, is obtained. No slip, or you will say stick condition, that is, we say the fluid sticks to the solid surface, it does not slip past the surface. So the stick, or what is known as an adherence condition, that's what Seren calls it. That means the fluid adheres to the solid surface. So in which case, what we say is that the V of the liquid is equal to V of the solid. Here, of course, I need only one component. I am writing the general expression for the no slip condition, where all three components might be present. Right? So what it means is that effectively the fluid adheres to the solid surface. That means it has the same velocity as the velocity of the solid. The solid is also moving. It could be, you could have a plate moving past fluid. So the fluid sticking to the plate, right, will have the same velocity as the solid surface it is in contact with. Right? So typically, no slip condition applies for liquids, but it might not apply for a gas. So if a gas is in contact with solid, the no slip may not always apply. Right? So, and Seren actually points out that this might also not apply when the liquid does not wet the surface. So in which case we cannot say the liquid adheres or sticks to the surface. But commonly, definitely for water and normal fluids, it's fairly, we all know that it wets the solid. That actually comes from the physical mediated properties of the interaction between the liquid and the solid. So typically, the no slip condition would apply. Right? Now, if you have a gas liquid interface or even a liquid interface, the condition that is usually applied is what is referred to as the continuity of stress, either like a gas liquid or even a liquid interface. What the condition is applied is that the stress must be continuous across the surface, because when you have air and liquid here, right? So there is the stress in the liquid, and then we have to also say that there is stress in the some stress. We are not actually modeling how the air is flowing or what is happening in the air. At the interface, there has to be continuity of stresses. Whatever stress is experienced by the liquid due to the air must also be the stress experienced by the gas due to the liquid, due to its contact with the liquid. Because stress is a contact force. So two fluids are in contact. Each one is exerting a contact force on each other. So what it says is that across the interface, the two stresses must be the same. That is what is called as the continuity of stresses. Now, how does it apply here? That is very easy to infer, right? The first condition, especially that the plate is not moving; it's an inclined plane, right? It is fixed. So clearly, at x equal to 0, dz equal to 0, that would be the form that the no slip condition will take. We are not considering those anomalous cases. The fluid might not wet the surface and all those things, be set aside. So this is clearly the no slip condition. That's how it would apply. Now the continuity of stresses would mean that x equal to delta dv sen by dx is equal to 0, right? At the interface between the gas and the liquid. So now we conclude that the continuity of stresses would mean this.
Shear stress is very low at that.
Yeah, shear stress. In fact, we have to look at now how the stress picture would look like, both within the liquid and at the interface. We'll come to that shortly. But what it effectively says is that not only the shear stress but the normal stress also must be the same, right? At the interface, which would mean effectively that the velocity, the derivative of the velocity with respect to x has to vanish, right? That is the condition that we get on the velocity component. Because if you look at the normal stresses, right? Let's just consider the liquid here. And if we consider an element of fluid here, let's say, and if you open the door, you have to open it. So, the condition of continuity of stresses would mean that that is true. Now, what do we mean? What the stress is actually this for us. It's not just the shear stress that we are considering. Since we have now got the rough qualitative form of the solution, we can easily see what form we know it's a linearly viscous fluid. We have got the velocity profile to within two arbitrary constants. We know what it depends on, so we can easily figure out, right, what the shear stress will look like. Actually, here I would have dxy, change the notation. Right? So now T is actually given by, we can have the tensorial form of this. So T would be minus Ti. T we have actually already determined, right? So this part is known. Plus D. Now what can you say about D? What would be the form? So this is when I write it in matrix form. This would be minus P0. 0 minus P0, 0, 0 minus P. P is actually a function of x. I can make that explicit. We know that P is now independent of y and z, right? Plus times. Now, if we were to write the complement, we have written this x. So this would be dv x by dx, what would this be? Half times the dij is half times bi comma j plus bj comma I, right? So that would be half dx by dy plus dvy by dx plus, not plus, that's all there is. What would be the third term? dvx by dz plus dvz by dx half, right? So to make it clear, because it's easy to look at it as 1, 2, 3, but all I have to do is to make this x, y, z. Right? So that would be half times and similar, this will be the same. So once you have written one half diagonal term, the other half diagonal term is determined. The diagonal terms are very easily written. You can see that the diagonal terms are all 0. So if I regard this, usually the shear stress is, so this is actually, the interpretation is that this will also be normal stresses actually, because they are also diagonal D11 is that the normal is in one direction E1. We are looking at the component in the E1 direction, so that's also a normal stress. So all the diagonal elements of D, but they are split into two parts. One part is coming from the pressure, the hydrostatic part. Other part is coming from D itself. Right? So the off diagonal elements are what are referred to as shear stresses. Right? So we see that there is no contribution at all in this particular case for the normal stresses on the deformation tensor, because all the diagonal elements are 0. Vx is 0, so this is 0. Vy is 0. Continuity equation says that dvz by dz is 0. Everything is 0 along the diagonal, and this would be half dvz by d1 to dvy by dz, and that is what you would also get here, and this is what you would get here. A whole lot of these terms are going to cancel, become 0. This is 0. This is also 0. Right? So obviously this is 0. This is also 0. So the only two terms that come in the off diagonal, they both equal to each other. This is dxz and dzx is what would come. Right? So clearly now I can write the d itself as minus p along the diagonal. This is now the entire stress tensor. So this would be 0, this would be 0, this would be 2 mu times I will have half dvz by dx, because dvx by dz is 0. So you can clearly see that the common way of writing, for instance, Newton's law of viscosity as tau equal to mu d, in this case dz by dx, it's only one component. It will applicable only for the one-dimensional flow. That those are the only shear stress components that are. This is all there is, and if you want, I can write this as everything is a function of x only. There is no other dependence, either y or z of any of the components. So this is the entire shear stress. So when we say that the across the interface is continuity of stresses, that means all of this at the interface, we know the pressure is the same, right, at the atmospheric pressure, so that is continuous. So we say that the shear stress which in the liquid is given by mu dvz by dx must equal the shear stress experienced by the air, right, also due to the flow of the liquid. And we say that because air is a very low viscous fluid, we would say that the shear stress is 0 for the air. Approximately, it can be neglected. continuity of all the stresses across the interface. The continuity of the shear stresses means that dV z by dx for the liquid at the interface must be 0, and I can justify this condition. So we are not talking about how, it doesn't mean that mu is 0, because for the air viscosity is 0. We are not looking at how, whether there is a velocity profile or what kind of flow the air is undergoing. But clearly the shear stress we are saying would be 0, whatever the air might be undergoing. Right? Because our focus is only on the liquid. Air comes into play because it is at the interface of one side of the liquid. Right? So if you see that the shear stress experienced by the air is 0, then the shear stress due to the continuity of stresses experienced by the liquid at the interface must also be 0. We clearly know that the mu of the liquid cannot be neglected. Right? So we conclude that dVz by dx must be 0. So that condition arises out of the continuity of stresses along the liquid gas interface. So you have to be aware, boundary conditions are always a problem and are often, there is no one uniform rule. You have to look at the particular fluids that are in contact with particular surfaces and then arrive. These are typical boundary conditions that come into play in simple situations. Right? So with these now, we can arrive at the solution. So the solution will now be given by simply solving for C1 and C2. So x equal to 0, Bz equal to 0 would mean that if I put x equal to 0, Bz equal to 0, that means C2 is actually equal to 0. Right? Now, dVz by dx is also 0 at x equal to delta. So I look at dVz by dx, when it is equal to 0 at x equal to delta, then I will get implies that C1 is equal to rho g cos beta delta. Right, so times x. So we have rho g cos beta can be taken out. Maybe rho g cos beta by 2 can be taken out, and x can also be taken out, and we will get this would be the solution. Bz itself can be written like this. So this is the final solution. So we've got the pressure I've already written it. So this completes the problem. So we've already pointed out the incompressible fluid. We need to determine both the pressure as well as the velocity. Right? So pressure I've already written that expression. You can write it down alongside this. This completes the solution. So clearly at x equal to delta or at x equal to 0, the solution Bz is 0, you can easily verify that this condition will also be satisfied. Are there any questions on this? Now we can use this information because we know the stress. We can look at the kind of forces experienced by the fluid. The velocity profile itself will be parabolic, right? So it will be 0 here. So it can be plotted in this manner. And we reach a maximum at x equal to delta. So the Vz at x equal to delta is given by so that will be the value, the maximum value. The shear stress will have the opposite behavior. The shear stress is actually maximum here, it can be easily shown. It actually becomes 0 at the interface, right? It will be a good exercise because we have the shear stress tensor, but what is actually of interest is the way the normal and the shear stresses act on the fluid at any point within the fluid. So we can know, for instance, I can consider as an illustration, I consider a rectangular volume element of fluid, right? At some point, let's say, given by x naught, y naught, z naught. Right? So I'll just plot that here. Here we've got ambit there itself. So this I would call, let's say, as delta x, and this I would call as delta z, right? And the y would be in, this would be delta y. I'm looking at the volume element within the fluid. So I can now look at what are the forces acting. So there are 6 faces to this rectangular volume element, right? And so let us look at the top face. Look at the top face. So you can now calculate the forces arising out of the stress, right? So the top face, the E we have already seen, D is minus B. The Vz is given by that. And B is a function also of x, that's very important. So if I want to calculate the force on the top face, the contact force. Down x z, but I want to calculate all the forces, right? So how would you calculate the contact force? You're not worried about the body force, of course, acting on the whole volume element, mainly the weight of the volume element, right? Times the density times the volume element. You're looking only at the contact force. How would you calculate the contact force on any surface? And you have the stress tensor. Yeah, area of the face is known. What is the formula that would give you the contact force? N dot T, right? So we have the general formula, but finally it amounts to the shear stress, the normal stress and all the stress component, the tensor. What we are interested is in the contact force, right? That is finally the quantity that we would directly associate force exerted or experienced by a body of fluid. Right now, look at the force experienced by this volume of fluid, right? So the contact force is going to act across 6 phases. So force experienced by this body of fluid due to the action of the fluid surrounding it. We come back to it and now we have a concrete example to evaluate or estimate these forces, right? The T is N dot T. So what is N for the top face? I'll just do it for maybe one of the top face and the side face. It's a good exercise for you to go and do it for all the other faces. And clearly the contact force itself is given by dA. What you said is correct. There is an area associated with the top face. So I need to calculate the contact force at every point, but because these are planar chosen these two, I can also consider a spherical volume of fluid. But for convenience, I have chosen it to be a rectangular volume because that's what we have dealt with so far. Rectangular coordinate system where this is easy to implement, right? So we know that for a planar surface, the normal is the same at every point. So for the top face, what is the direction of the outward normal? Ex, right? So n is equal to Ex. So what is Ex dotted with T? Right? Easiest way is we have seen that n dot T is simply, if we want to calculate this, I write n1, n2, n3 and multiply it by T, and then you get again a 1 by 3 matrix. So those are the elements of the new vector, right? So here 1 0 0, right? And I have T11 or Txx general, and then writing Txz, Tyx, Tyy. Right? So what would this be? This would be Exx and then Txy and Txz. Right? So that is the Ex dotted with T. That is the direction. So it has components not just in one direction, it has components in all three directions in general. So I can now write this in vector form as Exx, Ex. So that will be the X component. Right? I have to sort of take the transpose of that, then we'll get it in the column form. But I can clearly see that this would be the X component of the force plus right. But in this case, this would be very general for a plane whose normal is, for a surface normal is in one of the coordinate directions, which is what I have chosen it to be. Chosen the orientation so that it's along the Ex direction. This is a very general formula. Catch or capture three of the components of the stress tensor: Txx, Txy, and Txz. You can easily now infer that if when it is capturing the first row of the stress tensor, if we were to take Ey, then it would take the second, but you know that whatever may be the normal, you can easily calculate by calculating the dot product in this way. Need not necessarily be 1 0, because 1 0 0 brings in the first row, 0 1 0 would bring in the second row, 0 0 1 would bring in the third row, and you have a vector form like this. Right? Now, in this case, of course, Txx is minus P. It's importantly a function of x, right? Plus Txy is 0 in this case, but Txz is u dvz by dx that we have to calculate. So that is also a function of x Ez. So that is the force acting at every point on the top surface. And we notice the location of the top surface, the x doesn't change at all. And because finally I have to put this into the derivative. So what is dA for the top surface? It is dy dz, right? X doesn't change. For this, the area element is very easy to see from just the geometry of the figure. It would be simply delta y delta z. So actually I have to do, right? So I have to integrate this over dy dz. And x would vary from whatever to whatever value, but in this case, x is fixed for this element, right? So and since all of these depend only on x, so if it were dependent on y and z, then I would have to integrate, right? So this is at a particular value of x and over y and z. Actually, the limits are not from x to x, but from y to z. But since the integrand is independent of y and z, right, all I will get is in this case minus p x, where x is equal to, when take this to be x naught and this to be delta x, that would be at x naught plus delta x by 2, right? Plus mu dv, this is the x component of the force. That's the normal component. So this is the force in the x direction would be the normal force, and the shear force is given by, again evaluated times the whole thing would be multiplied by delta y delta z. That is the total contact force on the top face. Now I will consider for a change, because now this is very simple, because the x doesn't change for the components are dependent only on x, and the x value is fixed for this particular face, right? So it makes the integration that much easier, right? So now if I take, let us say, one of the side faces, right? Let us say the left face. So for the left face, n is equal to what? It will be Ez only, because the outward normal would be Ez, right? The outward normal is Ez, right? So now I have to calculate Ez dot t. You can easily prove that that is going to bring in the third row, right? If I choose for one of the front or the back faces, I get the second. I've chosen this, right? So you can prove easily. Right? So what we have here is 0, 0, 1 times t. So you can easily verify that that would bring in t zx dx plus t zy ey. Very important to consider these separately, because these are all components in the different direction. You cannot just add tzx, tzy and tzz. They are vector addition, right, and not just algebraic addition. So now in this particular case, tzz is minus p, right? So this is t. Zy is 0. Zx would be we have this. Now the important thing to remember is that for this phase, suppose this is T. So what would be the contact force? This integral d dA. So dA for this, right, is clearly dx dz, right? So whatever, let's now take just the x component, right? The ex component would be integral
dvx by dz.
dvz by
dvx by dz. dvx by dz. So that was dvx.
No, dvx is dx is 0. Both components are the same. D, the term D, we've already established that the two off-diagonal elements that would not vanish are both given by mu times dvz by dx. There's no question of dvx by dz here, right? You have to go back and think why that is the case. We've arrived at this after doing all those manipulations involving D and it being the symmetric part of D and so on. Right? So this particular problem, of course, for the general case, you will get actually half times dvx by dz plus dvz by dx. Here dx is 0, so you won't get that. So you are getting only the dvz by dx. So mu dv and x varies from x0 minus delta x by 2 to x0 plus delta x by 2. This is a very, the rectilinear integration is very easy to do. If this is oriented, even if the planar surface is oriented in an arbitrary direction, then it would be a bit difficult to do the integration. But here it's very straightforward. And this would be y0 minus delta y by 2. So this delta y should not be confused with the dy. The dy is the variable of integration. Delta y is a finite length, right? So clearly, this is important thing is that now this is a function of x alone, right? So the integration will be only over x. The integration over y can be easily taken out, and you get delta y times now we can substitute for dvz by dx and with mu dvz by dx. Interestingly, the mu would probably then disappear. So we get C1, right? We already see is rho g times cos beta times delta. So this would be delta minus x dx. So this has to be integrated. This is the contact force that you would get for the left face. Only part of the contact force. This is the normal part that we have to calculate. We have to put all of these together, so this can be easily integrated. So I'll make you do the integration. So this would be rho t cos beta delta x minus x squared by 2, and it would run from x0 minus delta x by 2 to x0 plus delta x by 2. Now for p, that also has to be integrated now, because that's also a function of x. Right? So wherever you have, the top and bottom faces, right, the x value is the same. The top face, the x value is x0 plus delta x by 2. The bottom face, the x is x0 minus delta x by 2. For all other cases, you have to integrate. The integration typically will be only over x, because in all the cases, the integrands, whether it be p or the shear stress component, are functions only of x. So wherever there is a variation in x, so this would be the left and right faces, and the bottom and the front and back faces. Right? Each one has to be done independently. So for p, the procedure would be the same. So the z component would involve minus p, for which we have the expression. So that would also be, right, minus the z component of the contact force would be minus times p of x, right? Again, x0 minus delta x by 2, x0 plus delta x by 2. The whole thing multiplied by delta y, because y, there is no variation of the integrand with respect to y. Right? So in the same way, if for instance I take the, well, we have to fix which direction the positive y is, right? It is x back side, right? So we can make this y. So clearly, for the front face, it would be minus ey, right? So you would get minus 1, 0, I mean 0, minus 1, 0 multiplied all through, and you get the middle row into the picture. So there again, the integration would have to be done from x. So let's keep that alone. So for the front face, right? N would be equal to minus ey, right? So I can write this in component form as 0, minus 1, 0. N dot E would be minus, right? So I want you to do this exercise for all the 6 bases and do all the integration and come and tell me what the answer is in the next class, because we won't have time to do it. But it's a good exercise for you to So this would be clearly the second row would come into picture. So that would be Dyx Ex plus Dyy Dy plus Dyz Ez. Right? Again, the integral. So what would this would be T? What would be T times dA? Right? So the integration here, we now covered all possible variations because the calculation for the bottom phase would be identical to the top phase except the x is changed. Similarly, the calculation for the right phase, right, would be different but be very similar to what we have done here. Right? So now we come to calculation for the front phase. The calculation for the back phase would be very similar. So the area element here is clearly delta x times delta z. So this would be whatever it is, dx dz. Now dz, there is no variation of any of the quantities with respect to dz. So this would be times delta z. And again it would have to be integrated. So integrate again is a function of x. There is a variation of the x value for the front phase from again x0 minus delta x by 2 to x0 plus delta x by 2 to complete the calculation. Right? So we have to then complete the calculation for all the 6 phases and finally gather together the answer for each one of the phases. Right? Then we'll check the answers in the next class. Are there any questions? For what? No, contact force, see, the normal for each of the phases is different. So we have to do the contact force because E xtn dA. The reason we are doing for the 6 phases separately is that the n for each of the phases is different. So I have to calculate the contact force separately for, you see, and then we can do it as the divergence of the stress tensor over the volume. Yeah, we can do it, but it's also illustrated to see how the forces are, that will give the total force on the whole. Using the divergence theorem, you can calculate that. I'm not denying that, but what I'm saying is that this is still illustrated because you see how the different forces are acting on each of the, at least 3 phases. Because there are 3 phases oriented along the coordinate direction, and 3 other phases in the negative coordinate direction. So you can see what components are actually contributing. Right? So they are interested not only in the total contact force but also the way the contact forces are acting on each phase. You can try that. You can use the divergence theorem and calculate that and match the two. That would be another exercise. Right? Any other questions? Right? So for the quiz, we still have some time left. For the quiz, I am not going to include the special problems that we have started discussing. Quiz will include all functions right up to the general equations for a linearly viscous fluid. Special problems are the many we have just started, so I don't want to include that for the quiz, which will be next Monday. Okay, so whatever we have covered up to the, of course, it's always possible for me to ask you to calculate the stress in a particular phase or whatever, because that is part of the general scheme. Because I am simply using this equation which has been covered long time back, but the emphasis will be on general principles rather than solution of specific problems will not be there. But I can always give you the state of stress, maybe not in this form, but in some other form, and ask you to calculate the contact force acting on a particular area, element or whatever. That would be there. Special problems for linearly viscous fluids we are not going to include for the, which would include you to solve the equation of motion and get the solution. That is not part of the quiz. General principles are there, including portions we have covered for the constitutive equation for the linearly viscous fluid. That would be there. We would focus largely on vector and tensor identities, and which may be for a general vector and tensor or ones that are familiar with fluid mechanics. We give A, B and C are given in terms of velocity and various other quantities associated with fluid mechanics. But the emphasis will be on your comfort level with the basic operations involving vectors, tensors, the various dot products, cross products, right? And on top of it, the gradient operator, the divergence of a vector, the divergence of a tensor, the gradient of a vector, the gradient of a scalar. All those operations in rectilinear coordinates you should be very thorough with. So the quiz will largely focus on that. Test of basically assignments 1 and 2. If you're comfortable with, then you should be able to do it quite easily. Right? Any questions? Other questions on the quiz or what has been covered today?
Sir, this is not valid for turbulent viscous fluid.
Viscous laminar flow, yeah, we haven't even defined what flow is. I mean, how to arrive at that, but based on these assumptions, this is what we will get. Also, we have to take it upon other effects which we have not considered so far. Right? So we'll take that up later on in the course. So if there are no questions, then we'll meet again on Thursday. I want to take up this in detail and I want you to work through this. It will still be very useful for your quiz because these are for very general calculations and it involve how to calculate the stress vector given the stress density. So you should be comfortable with that. So I would like you to try that for all the 6 phases and see what you are getting. You can check the answers on Thursday.